Hello, we are from Group 2. The purpose of this video presentation is to present the simulation project and explain the operation of each block. The first block is the sine wave block. It is used to create a multi-channel real or complex sinusoidal signal. The sine wave block is connected to the switch block. Next, the Bernoulli binary generator block have been used. Commonly, we use this block to produce random data bits. Then this is the second sine wave, which practically same with the first one. This is the switch block, which is based on the value of a third input term. The control input propagates one of two input to its output. Other than that, there is a change pump block. It's used in the changes the phase of a locally produced signal to match the phase of an input signal automatically. Then this is the constant block. It helps to create a signal with a real or complex constant value. And lastly, we set the relational operator block with less than symbol.
Okay, now I'm Jacob JILOM Lawrence who would like to explain about the waveform signal of frequency shift keying waveform signal, FSK. So, as been told or been explained by Irfan Rosli just now about on how to get the output signal for FSK. And now, what we see at this column, the black one, this one, is the interface of the scope. And here, as you can see, on the top one, signal is get from this connection, which is it's connect from Bernoulli binary generator connect to the scope. And this middle signal is the modulating signal, which is get from this connection. And the bottom one, this signal is get from this connection. Okay. As what we can observe from this output waveform signal, the message signal is similar to the demodulating signal. It's almost the same, as you can see here. It just a slightly different, which is on here. For the message signal, it's from column 0 to 1, 1 to 2. But for the demodulating signal, it's from 0 to 1 and 1 to a bit more than 2 around here. But the difference we can see is the modulating signal, the shape of the modulating signal. That's what we can see here and here. The gap between the line of the waveform is different. In short, we can say that there is no gap when the digital input is 1. At the column of when the digital input is 1, there is no gap between the line of the waveform signal. And when the digital input is 0, there is a gap between the line of the signal. This we call is space frequency. When the digital input is 0, there is space frequency. But when the digital input is 1, it's called as mark frequency. Okay. The gap, this one, is smaller than this one. It is continued repeatedly based on the message signal. When the message signal, the column, the section is until here, so the mark frequency is until here. And when the digital input is 0, at the section of digital input is 0, it's at this column, and same to the next one and to the last one. And the bottom one, the demodulating signal, also almost the same with the section of the above of the modulating signal, as you can see here. Okay, I think that's all for the frequency shift keying waveform signal, and I would like to pass to the next presenter to present about the QAM signal. Thank you.
The quadrature amplitude modulation started with the assembly of various blocks from the Simulink library browser. This is the random integer generator block, which create evenly distributed random number. The number of elements in set size correspond to the number of independent channels output from the block. The general QAM modulator baseband block is used to modulate the signal using quadrature amplitude modulation. The output is a baseband representation of the modulated signal. The AWGN channel block also been used. In this block, white Gaussian noise is added to the input signal. The general QAM demodulator baseband block was used to demodulate a signal that was modulated using quadrature amplitude modulation. Two sine wave blocks were used to produce sinusoidal waveform. The amplitude for the sine wave 1 block was set to 2. Then each of the sinusoidal wave were added to product block, which to produce the result of multiplying two input. The modulating signal was entered the complex to real imaginary block to form the real and imaginary part of the input signal. Meanwhile, the amplitude for sine wave 2 block was set to 1. The result of two waveforms that had been multiplied with the sine wave then were added using sum block to perform addition on its input.
My name is Muhammad ZULFARHAN bin SABRI. Now I want to explain the simulation of QAM modulation technique. Basically, in our simulation, we have totally 12 blocks that function to generate the message digital input, modulating signal and demodulating signal. QAM is a better modulation technique compared to FSK. So, in this part, I will show how to generate QAM modulation technique by using block in Simulink. For the first blocks, to generate a random digital input, as you can see from the scope, there are various of input data that generate randomly. Basically, this digital data is a message signal that we want to transmit from the transmitter. In our design, we are using 8 as such. That's why we have the digital data from 0 until 7. For the modulating signal, general QAM modulator was used to obtain the modulating signal, but QAM modulator generate the signal in digital form. Because of that, we don't want the signal in digital form. That's why we need to separate the signal into the real and imaginary by using the complex to real imaginary blocks. After that, we combine the sine wave with the amplitude 2 volt to the real and combine the sine wave with the amplitude 1 volt to the imaginary. After that, we plus these two combination and we got the QAM modulating signal that's suitable to transmit from transmitter. As you can see in the scope, the QAM modulation signal is a combination of the amplitude modulations and phase shift keying according to the data input that we set up. In this signal also have a carrier signal and message signal, where carrier signal is come from the sine wave block and message signal is come from the random integer block. For the modulating signal, in general, demodulating is function to change the modulating signal to the original signal. As we can see here, the signal obtained is almost accurate with the original signal from the digital input. Before demodulate the signal, we are adding AWGN channel to add white Gaussian noise to the input signal. In this AWGN signal, we set the dB/NODB equal to 100 to get the better demodulating signal. So the modulating signal is accurate almost 100% with the data input. So I think that's all for the QAM modulation. Thank you.